Hi, this is Dr. O'Connor. Welcome to Pathways to Chemistry. Here we have another buffer problem, and we're told that a buffer is prepared by mixing 50 milliliters of 0.05 molar sodium bicarbonate with 10.7 milliliters of 0.1 molar sodium hydroxide. We're asked, what is the pH of this buffer? Well, first thing we have to realize is that the hydroxide ion is going to react with the sodium bicarbonate or the bicarbonate ion to produce the carbonate ion, and there'll be some water in here, and I'm just writing the net ionic equation here. Okay, we're also going to have some sodium ion in here too, but we're interested in the reaction of the base, the hydroxide ion, strong base, with the bicarbonate ion to produce the carbonate ion. Now, first thing we need to do is find the number of moles of each species that's involved here. So the moles of bicarbonate ion are going to be equal to the volume in liters times the molarity of the bicarbonate ion. And that will be 0.0025 moles of bicarbonate ion. And of course, the number of moles of sodium hydroxide or the hydroxide ion would be the volume of hydroxide that's added. So that's in liters, that's 0.0107 liters times 0.1 mole per liter. And that's going to give us 0.0107 moles of hydroxide ion. So the next thing that we should do is go ahead and set up a table. First, I'll write the reaction again. So we have the bicarbonate ion plus the hydroxide ion to produce the carbonate ion and some water here. Okay. What we need to do is determine the number of initial moles, the change in the number of moles of each species as the reaction proceeds, and then the final number of moles of both the acid and the conjugate base. So initially here, what we have is 0.0025 moles of bicarbonate ion. And we add to this buffer 0.00107 moles of hydroxide ion. And then, of course, here we have no carbonate ion initially. Now, what we have to realize is that all of this hydroxide ion is going to react with the bicarbonate ion. So at the end of the reaction, we're going to have 0, the hydroxide ion. So we'll go ahead and subtract. Again, we have a 1-to-1 mole ratio here, 0.00107 moles from the initial number of moles of bicarbonate ion. So 0.0025 minus 0.00107. That's going to give us 0.0014 moles of bicarbonate ion left. And remember, as the base, the hydroxide ion, reacts with the bicarbonate ion, then we're going to have this much 0.00107 moles of carbonate ion produced. Okay, so now we have all we need to find the pH of the solution. One more thing that we need, we're going to be using the Henderson-Hasselbalch equation. So we have pH is equal to pKa plus the log of the quantity concentration of base. So that's, or I should say conjugate base. So that's the carbonate ion over that of the acid, which is the bicarbonate ion. Okay, so we need the pKa. Well, we have Ka, so pKa is going to be the negative log of the Ka, 4 times 7 times 10 to the negative 11, and that is going to be 10.33. So now I have all of the information that I need in order to determine the pH of this buffer solution after this strong base has been added. So our pH then is equal to 10.33 plus the log of the base acid ratio. So here we have 0.00107 moles for the base and 0.00143. Erase that. Moles for the acid. Remember, when using the Henderson-Hasselbalch equation, we don't need to use concentration. We can just use the number of moles. The ratio of the moles of base to acid that counts. Because remember, both the acid and its conjugate base are in the same volume. So the volumes would just cancel. And our pH then is 10.20.